Thank you for the introduction. The room is a lot more sparse than it was on the first day, but that's okay. So I'm Kangbo. I'm a PhD student from Cornell. And today I'm presenting this library for making readable and simple electronic structure libraries. The story behind this is that when I started my PhD, my advisor gave me two options for a project. One of them is community detection, and the other one is this Kohn-Sham density functional theory. And for some reason, I thought density functional theory is easier. And so I think the reason was that the formula that describes the theory is very simple. It's just 2 lines of formula. But of course, it's not very easy to implement in practice. And I think the reason for that is because a lot of the complexity are hidden in the indices here. So here there's K and there's R. And so if you are familiar with condensed matter, K is a K point in the first Brillouin zone, and R is a point in the unit cell. It doesn't matter exactly what they are, but they are not integers. And that makes these 2 lines of formula quite difficult to implement. And so later on, I focused my research on this thing called localized one-year functions, and there I encountered the same problem. You have 2 lines of formulas that looks very simple, but then you have this shenanigan of K and R and B that there's a lot of headache to deal with. And so I learned a bit more about electronic structure later on in condensed matter, and it seems that this is a recurring theme. It's a problem that happens all the time. And for example, if you look at Berry phase and Berry curvature in the context of electronic structure, it's the same problem. Very simple formula, but complicated to implement. And that happens even for simple spin models as well. So if you have a nearest neighbor coupling Haber model, you still have this difficulty with implementation. And I think that's part of the reason why people like 1D chain of spins, because once you have a general higher dimensional model, you have to deal with these indices, and they're quite difficult. So that's the motivation behind this work. The subscript in the theory is a very complicated part. But if we were to imagine that these indices K and R were just integers, then you have the objects such as U and KR. It would just be a simple tensor. And within Julia, you have excellent packages like iTensor and Tulio and the tensor operations. And at that point, the problem is a lot easier. So that motivates this package. So that's WTP.jl. It provides an abstraction for a point on a non-orthogonal and periodic grid. And what this basically describes what sort of object K and R are. And to give you some example of non-orthogonal and periodic grid without explaining the details because of time, if you're familiar with the Brillouin zone, that is a non-orthogonal and periodic grid, and also the crystal lattice. So if you did material science, then you have this crystal lattice that's also non-orthogonal and periodic. And then if you look at the unit cell, and if you define a wave function on the unit cell, and with some sort of discretization, is also an instance of this type of grid. And then there is the reciprocal lattice. And so the first 2, so these are for different grids that are commonly used in electronic structure, but the abstraction that describes them can be exactly the same. And in fact, the first 2 grids and the second 2 grids, they contain exactly the same information, just in different form. So to deal with this, WTP provides some abstraction. so we want to have this point on a grid to behave like a subscript, so that you can write down expressions like this, right? You have some sort of wave function, and you can index it with k and r, and simultaneously has to behave like a vector in 2D or 3D or more, so that you can do things like finding the nearest neighbor. And then you also have to support this periodic boundary condition to have the right physics in electronic structure. For example, this class scattering in the context of if you're in the momentum space. And in the end, it also has to support non-orthogonal bases, so that you are not restricted to cubic unit cells or square unit cells. So
can you speak directly into the mic, please?
Yeah. So here is a little demo of what these abstractions look like. So if you are starting with, so this is the lattice for graphene. It's a hexagonal lattice. So each gray box is a unit cell, and these A1, A2, they are the basis vectors. And so you can create the grid given these two, given A1, A2, these are the basis vectors. And then you tell it how many replication you want for the unit cell. And so that gives you this crystal lattice. And because the crystal lattice describes the same information as the Brillouin zone, we have a procedure that gives you the Brillouin zone from the crystal lattice. And so a grid is really a collection of grid points. So it should support, it is basically iterable. It supports the iterable interface. So you can get a grid point by indexing a grid to get this, to get a k point. And because it's iterable, you can also map something on it so that you have a function or a tensor defined on a grid. And here is really where the abstraction is. So if you have this sort of a function on a grid, you can use a grid point directly as the index. And this sort of notation allows you to abstract away the fact that k is not an integer. And underneath, what it's doing is just there's a procedure that converts this grid point to an integer, and they just index the underlying array with it. So the other abstraction is that the grid point also has to be a vector. So it should support basic arithmetics, so that you can do things like finding your nearest neighbor if you want nearest neighbor coupling. And then you have this, you should be able to find the Cartesian coordinates and of the grid points. You should also be able to get a grid point from the Cartesian coordinate given the Brillouin zone, given the grid as the context. And the last thing is that it should support periodicity. So if your arithmetics takes you to a point outside the grid, it should be able to detect that it's overflowing, and you can reset the overflow to fold it back into the, let's say, first Brillouin zone. So that's the package. And so what we did after that is that we implement this CDM.jl, and that's our localization package. And basically, so this is a code snippet from that package that implements these two lines of central equations in the theory of localized linear functions. And you can see it's basically 5 lines of code. And this used to be 300 plus lines of Fortran code in this famous package called 190. So the take-home message is that electronic structure code can be simple if you have the right, can be greatly simplified if you have the right abstraction for the subscripts. So this is my email, and any feedback on this is very welcome. That's everything.
Okay. Thank you, Kangbo. Is there a question?
To my best knowledge, this one-year functions is usually not unique, right? So how do you solve this uniqueness of your one-year functions? And did you try to reproduce those one-year function results back into Fourier transformation and compare with DFT results?
So the uniqueness is something called the maximally localized one-year function, and it's called maximally, but it's not really maximally localized. There is no proof for that. But basically, you define an objective function and you minimize that objective function with respect to the non-uniqueness you have to make it unique. And that's what 1-year 90 does, roughly speaking. And that's what we are doing.
Okay, thank you.